start to
recording.
Okay, good afternoon, good morning, and good evening, everyone. So it's my great pleasure to welcome you today in this talk by Professor Emmanuel Trelat. Professor Emmanuel Trelat is a full professor at Sorbonne Université, and he is the head of Laboratoire Jacques Lilians in Paris. And today he's going to talk about approximate control of parabolic equation with on-off shape control by Fenchel duality. So, Professor Emmanuel, thank you very much for accepting deliver again a talk in our seminar, and thank you, and you have the word.
Thank you very much, Diego, for your kind introduction and for this new invitation to your seminar. I am very glad and honored to take part to this anniversary version of your online seminar. And I congratulate you and all organizers for this very nice online seminar. So I'm very glad to have the opportunity to present you this recent work that was done with Camille Pouchol, who is in Paris, Université Paris-Cité, and with Christophe Zhang, who is in Nancy currently in France. So the topic, as you said, is about approximate control for some parabolic equations. Let me present you the framework. Let us say that you are, as usual, on a bounded open subset of RD sufficiently regular, and let's say that you consider something like the heat equation, the very usual heat equation on capital omega with Dirichlet conditions at the boundary. And now we will put some control inside this equation at the right side member of this equation. But as you can see, the control is not in the very usual form, right? Because I will assume throughout the talk that the controls that we are allowed to, with which we are allowed to act on this system are of the form. So the product of an amplitude, capital M of t, which is, let's say, a non-negative amplitude, a non-negative function, right, times the characteristic function of some subset, small omega of t. So here, the characteristic function, chi omega of x, is the function which is equal to 1 whenever x is inside omega, and which is equal to 0 when x is outside small omega. And small omega of t is a subset of the domain, capital omega, that is also varying in time, as you can see. And so it's a measurable subset of which we are going to limit the measure. So let us say that throughout the talk, we fix a real number, capital L, which is between 0 and 1. And we are allowed to choose a measurable subset, small omega of t, depending on time, that is of Lebesgue measure less than or equal to capital L times the volume of capital omega. So it's a bit similar, this control is a bit similar as a heater that you can see on this picture. And in some sense, you want to act on the temperature in a room, capital omega would be a room, right? And you have a heater with wheels like that you can move throughout the room. You can put it everywhere. And you can tune, capital M of t, the amplitude, is that you can tune actually the heater. You can act on the choice of the temperature that you would like to reach with a non-negative amplitude, again, and let me insist on that. But not only, it's not a completely usual heater, so the similarity stops here, because also you can act on the shape of the heater. You can choose it completely. So, okay, you can, the heater could even have, why not, several connected components, okay? the shape of the heater, you can act on it, you can choose it in time. So here is this control system that we consider throughout my talk. Also here, for convenience and to fix ideas, I consider the usual heat equation, but as you will see throughout the talk, you can replace the Dirichlet Laplacian by some more general operator A. I will. And so now the question that we want to investigate throughout the talk is the following. It's the question of approximate controllability with such specific controls that we have called on-off shade controls. So the question is, you are given a final time, capital T. You are given an epsilon, let's say a degree of accuracy. You are given an initial state, y0, which is in L2. Now you are also given a target state, which is also in L2, yf. And you wonder whether there would exist a control. So do there exist an amplitude function, a non-negative amplitude function, and also some subsets, small omega, satisfying the constraint and depending on time, such that with such a control, you indeed almost reach with an epsilon at time t, the target yf. So it's the question of epsilon approximate controllability with such specific controls. Now, let me, on this slide, recall some very usual things, because certainly we are much more used to this form of internal controllability. So here you can recognize the usual heat equation with a usual control, which is the product of some function f of t and x, which is maybe not negative, which is also depending on x, right? It's not only a pure amplitude as previously. It has no sign, no constraint, times the characteristic function of some, let's say, fixed subset, small omega, of positive measure in capital omega. Okay, so the controllability problem for this kind of system is well known, and there are some known results since a long time, beginning with approximate controllability that is always true in the space L2, and that is known since many years. And even exact null controllability is known since 95, independently by Lebeau-Robiano and Emmanuel, right? And their results show that exact null controllability can be achieved in arbitrarily small time capital T with function controls that are function of T and X and that are in L2. Now, what is the difference? Here, the first difference is that we want to have non-negative controls. But not only that, actually, in my talk, we want also controls that are non-negative and that with amplitudes that do not depend on x, right? But already, let us look at what happens to this classical framework whenever we want now to impose non-negativity on this classical control. So then it is a much more recent topic, and there are very few results to my knowledge. And actually, as you can immediately see, there are some abstractions for controllability, just simply due to the comparison principle, because you see, as soon as the control function, which is that function, as soon as the control function is non-negative, then by comparison principle, you must have that the solution of the corresponding heat equation must be greater than or equal to the solution with control equal to 0, right? So automatically you already have an abstraction to controllability, right? And so it is not surprising to observe that indeed some states may be reachable, but maybe only for capital T large enough, meaning that you may require a minimal time in order to reach some targets. And also some other targets are maybe never reachable in any time. So this is the first big difference, let's say, with the classical situation, which is just due to the fact that we impose a sign to the control, right? But this is not the only difference, because in my talk, the control has a more specific form. It must be of the form capital M of T only, not of X, times the characteristic function of some subset that you will anyway allow to move in time. Otherwise, you would have only very little control and you wouldn't do anything. Now, what is the result that we have obtained recently with Camille Pouchol and Christophe Zhang? So here is the main result. There are two parts, part A and part B. So the part A is, let's say, a positive result, and the part B is a negative result, an abstraction. Someone is writing. Okay. So part A is on non-negative on-shape approximate controllability. So it says that whatever capital L may be, capital L, you know, is the fraction of the domain on which you can put some controls. Whatever the final time capital T may be. Now, for every epsilon, and for all states, y0 and yf in L2, such that yf is greater than the semi-group in time capital T applied to y0, right? Remember, it was the previous basic abstraction to controllability I was telling you, basic abstraction. And now it becomes actually a kind of sufficient condition to controllability. Then the claim is that there exists an on-off shape control that is a pair of controls, a function capital M of T, which is non-negative, and a subset, a path of subsets, small omega of T in the domain, satisfying the Lebesgue measure condition, such that the corresponding solution of the control system, starting at y0 at the time 0, almost reaches the final target, yf, at time capital T. So this is an epsilon approximate controllability result. And let me tell you already now, maybe not waiting for the conclusion, that we do not know currently, we do not know if exact controllability could be achieved. We do not know. It's a very interesting question, by the way. Now, the second part of the main result is an abstraction result. Now we assume, moreover, that the subsets small omega of T on which we control the equation are constrained to avoid a region of the whole domain capital omega. Okay, it means that, okay, you can move the heater in the room, but not everywhere. You forbid yourself to put the control, at least in some subregion of the domain capital omega. Then what we are able to prove in that case is that the above approximate controllability property is cannot be satisfied in arbitrarily small time. That is, there is at least a positive minimal time, which is so a new phenomenon. But in that case, unfortunately, we do not even know if approximate controllability would hold, however, in sufficiently large time. we are unable to prove that. We are just able to prove this abstraction. That is, there must be a positive minimal time. Okay, so now let me bring some comments on this pair of results. I will start with comments on the statement B. So first of all, and as I told you at the beginning, this statement can be extended to more general operators. The statement B can be extended to second-order elliptic operators. Okay, it's not a big surprise. And the second comment is rather on the proof itself. I will not give you the proof, but I will just point out that the proof is not based on the usual argument based on the comparison principle, as maybe you would expect. No, it's finer than the comparison principle. Actually, it relies on an optimal control argument, which is finer. Now let me comment on the A part of the main result, that is epsilon approximate controllability. Also, this part of the result can be extended to much more general operators than the Laplacian. Namely, it holds true for all operators on L2 generating a C0 semigroup such that, first, the operator dt minus A star is analytic hypoelliptic. That is, if you solve dt minus A star applied to U equal V, and if V is analytic, then U should be analytic. So, for instance, this is true, of course, whenever you deal with a second-order elliptic operator with analytic coefficients. The second property that A must satisfy is a kind of uniqueness continuation property. Namely, for every state Y in L2, if there exists a time t such that the dual semigroup S of t star applied to Y is a constant function on capital omega, then Y has to be equal to 0. So you see, it's not exactly the usual continuation property. It is something which is weaker. And this kind of strange continuation property is true as soon as the three following properties are true. So let me quote them. The first property is a kind of smoothing property, namely that if you apply in positive time the dual semigroup to some element of L2, then the result should be in the domain of S star. Okay, you have at least a bit of smoothing in positive time. Of course, this is true as soon as the semigroup is analytic. Second statement, the only constant function in the domain of A star must be the zero function. So, for instance, this is true for the Dirichlet Laplacian. But this property is not true for the Neumann Laplacian. So, for instance, we do not know in our context, and for the moment, we do not know how to treat the Neumann Laplacian because of that. And the third property that is required is the injectivity of the dual semigroup in positive time, which is, of course, always true for groups, or always true as soon as the operator satisfies a comparison principle, for instance. Right, so these are the various extensions. But you can keep in mind the heat equation, which is a very good example. Now, let me comment a bit still on the elements of the proof before coming to more details. As I'm going to explain, the proof is based on the Fenchel-Rockefeller duality theorem that I will recall next. But what I'm going to show is that we will apply this very celebrated theorem to a rather unusual functional, which is this horrible functional that you can see here. Capital F of U is equal to, you see, some kind of maximum between the L infinite norm of U and of some L1 norm of U to the square, plus some indicator function of U. So the indicator function is recalled here. Delta of U will be equal to 0 where U is non-negative and plus infinity otherwise. Adding actually this indicator function encodes the fact that in our problem we impose some non-negativity constraints. Actually, it will result from our proof that the controls that we will build have actually a constant amplitude, that is the capital M of T will be constant. And even more, actually the argument of proof is completely constructive. It gives explicit controls, achieving epsilon approximate controllability, in the form of some level functions which are attached to some adjoint equation. I'm going to explain a bit more now. So first of all, let me recall several known facts on Fenchel duality. First, if you consider a convex and lower semi-continuous functional on a Hilbert space capital X, so I call it capital F, right? The Fenchel conjugate, let me recall, is defined by this formula, the supremum over X of Y scalar X minus capital F of X, the conjugate, Fenchel conjugate. For instance, these two examples will be useful. For instance, the Fenchel conjugate of a square norm is equal to itself, or is equal to the square norm. And the Fenchel conjugate of the indicator function of the unit Bohr is equal to the norm. Actually, these are the two examples that I will need in what follows. Now, what is well known in Fenchel duality is that the double conjugate of F is always equal to F. This is Fenchel-Moreau theorem. And certainly the second theorem that is well known in this theory is the Fenchel-Rockefeller theorem, which relates the so-called primal problem with the dual problem that are written here. So the primal problem is defined as the problem of minimizing, as you can see, the sum of two functionals, capital F of X plus G of AX, where A is a bounded operator between two Hilbert spaces. And you have here the dual version of it, okay? And the Fenchel-Rockefeller theorem says that under a very, very slight assumption, you always have that the primal optimization problem value coincides with the dual one. And moreover, the primal problem has a solution if the value is finite. Moreover, you even have characterizations of the optimizer in terms of the subdifferentials of the conjugate of F and of the conjugate of G. So it is a well-known result that is well known in non-smooth optimization in particular, and which has been used many, many times in the existing literature. And actually, it has been used before in control theory. And this is what I'm going to explain now. In a paper by Jacques-Louis Lyons in 92. And maybe this paper, which I find very much remarkable, is not so much well known, maybe. Let me recall the context. It's a remarkable paper in which Jacques-Louis Lyons was able to characterize approximate controllability. Let me explain, because essentially, then with Camille Pouchol and Christophe Zang, we built on this very beautiful idea by Jacques-Louis Lyons. And we adapt it to our context. So the context is the following. Let us consider an abstract control system in infinite dimension, right? In a Hilbert space, y dot equal to ay plus bu, where b is a bounded control operator. You start at 0 at the state y0. Then the final state, y of t, is by the duhamel formula given by semi-group at time t applied to y0, plus this operator that is very usually denoted by capital L sub capital Tu, right, which is the integral part in the duhamel formula. Okay, so now the remark by Jacques-Louis Lyons is that what does it mean what does it mean to approach the target yf at the accuracy epsilon? It means that the y of t belongs to yf plus epsilon times the unit Bohr. Or, in other words, using this operator capital LTU, it exactly means that LTU belongs to a point, which is this point, y bar, plus epsilon b. Now, this is exactly equivalent to epsilon approximate controllability. And now the strategy by Jacques-Louis Lyons was to say, okay, now it is natural to search a control U solution of, to search a control U realizing the epsilon controllability as the solution of the following optimization problem. Namely, you will want to minimize the L2 norm of U under the constraint that LTU belongs to y bar plus epsilon b, because this constraint is exactly equivalent to the fact that y at time capital T is epsilon close to yf. So you see that this problem can be exactly settled in the form of a primal optimization problem for the Fenchel-Rockefeller duality theorem. Indeed, it exactly consists of minimizing the sum of two functionals, okay, capital F and capital G of LTU, where capital F is just the square of the L2 norm of U, and capital G is the indicator function of the set y bar plus epsilon b. Let me recall that this characteristic function applied to y is equal to 0 when, oh, there is a misprint, when y belongs to y bar plus epsilon b, and is equal to plus infinity otherwise. Okay, so it exactly encodes the fact that you are epsilon close to the desired target. Then what Jacques-Louis Lyons said in his beautiful paper is that, well, he computed the dual problem. So here it's not difficult because you just have to compute the Fenchel conjugates of capital F and capital G. So the Fenchel conjugate of capital F is itself right? Because it is the square of a norm. And the Fenchel duality of G, this is the Fenchel duality of an indicator function, and you obtain this formula, you obtain the norm. And so the dual problem is the problem that is written here on this line in red. And for those of you who know the Hilbert uniqueness method, it's almost the same, as you can see, except that here, instead of dealing with exact controllability, we deal with epsilon approximate controllability, but you can easily recognize here the very usual HUM functional, right? Which is related to L2 optimal control, as you know. And then what Jacques Williams did in his paper is to say that this dual problem has a unique solution, and the control, which is written here, which is exactly the same as in the HUM method, does the job, that is, solves the epsilon approximate controllability problem. Okay, so this was a summarize of Jacques Williams' work in this paper in '92. And so what we did with Camille and Christophe was, based on this very beautiful idea, we wanted to change the functional capital F. Because as you can see in this work, Jacques Williams chose of course, the simplest possible functional capital F, right? It is very good, because when you choose the square of the norm, the Fenchel conjugate is very easy to compute. And he obtained this beautiful characterization. That's okay, but our question with Camille Pouchol and Christophe Zang was, okay, but what could we do if instead of this functional capital F, we would choose something else? And this is how we came to this problem, actually. And well, I'm telling you the story exactly in the converse way, right? As we always do in mathematics, you present the result, but to come out with this result, you wrote plenty of drafts. Okay, so I tell you the story in the converse way. Anyway, the idea is to replace the square of the norm by this horrible functional, capital F. Why this horrible functional? Because it does exactly the good job. This is exactly the functional that encodes all the constraints that we want to put on the control. We do have here in our work a very specific form for the control. And so my claim is that if we now compute, actually, I will not go into detail here because it is too much painful, right? But it's perfectly feasible, believe me. You can compute the Fenchel conjugate of this functional. Okay, you obtain a certain functional, which is written here in green, which can be expressed using rearrangements in particular. And the claim is then that if we solve the dual problem, then we get also an adjoint equation, because it is an optimal control interpretation, right? And the unique solution, the unique control U star, that must be in the subdifferential of the Fenchel conjugate of F, is exactly of the desired form. That is exactly of the form a real number which is non-negative times the characteristic function of some subset small omega of t, which varies in time and which satisfies the measure constraint that was imposed at the beginning. Moreover, this optimal subset is given as a level set with some specific functions to characterize it. Okay, So maybe I will not go much further in the details because it's not much. I think it's not much necessary. So I will jump. I think I will jump directly to the conclusion. So in the conclusion, I would like to stress that we are not able, for now, to treat the Neumann boundary condition. As I said, this is because at some point we need some unique continuation. And so we need that somewhere at the boundary, we have some zero that you can propagate inside. So at the moment, we do not know how to treat Neumann boundary conditions. What we have done here, and that I have presented throughout my talk, concerns internal controls. Very likely, the same kind of result should be valid also for boundary controls. Although in that case, you would have to deal with unbounded control operators, which will thus imply some more technical statements, probably. More techniques are to be used, certainly. But I would say that the main question that is very much interesting and that unfortunately we are not able to answer for now is the question as to whether this kind of control problem is or not exactly controllable. And this we really do not know. We do not know if we can expect or not an exact non-negative controllability. Somewhat related to this open question is certainly also the cost of approximate controllability as a function of epsilon, when epsilon is going to 0. Of course, we do expect that if this cost does not blow up as epsilon is going to 0, then there should be a limit, and then we should be able to expect to have exact controllability, but we really do not know. And also, so maybe I will not talk about that, but also another question is, of course, going to numerics. And certainly this is also quite, we do expect that this is a delicate question, as it was for the numerical implementation for the HUM method. There has been plenty of works about this issue of implementing HUM, in particular by Enrique Zuazua, as certainly many of you know about this kind of result. And here, since our controls are even more specific than in the classical HUM method, we do expect, of course, to have to meet the same obstacles as in the usual HUM method. But we have not attacked this question for now. And I think that's all. Thank you very much for your attention.
Okay, thank you very much, Emmanuel, for your brilliant, amazing talk. So we open now the turn for comments, questions. So if anyone has a question, please, you can do it. Okay, Emmanuel, someone is Fuad et Tari. Thank you very much for your presentation. In the main result, the omega region is of uniform measure. What if L depends on time?
Yeah, it's a good question. So I think that I will not make a mistake by telling you that if in the functional instead of capital L you put a capital L of t, then it should work. I hope so. I hope so. As far as I have the proof in mind, I think that the time throughout the application of the Fenchel-Rockefeller duality theorem, the time does not play a big role and so I think that it is harmless to add capital L of t inside of it. I hope so, and it should work.
Okay. I have you mentioned the case of a Neumann boundary condition. I wonder if is it possible to get a similar result if you have a mixed boundary condition? I would say in part of the boundary you have a Dirichlet,
Yes.
in a part Neumann. Is it?
Yeah, and in that case it works. I mean, if you take a connected domain, capital omega, and if at least on an even small part of it you have some Dirichlet condition somewhere, it's sufficient.
Yeah, because in this case the constant solutions are zero, right?
Yeah.
Okay.
Yeah. It is really when you impose Neumann everywhere. In that case, I do not know. But you see, it seems like a kind of technical restriction.
Mm-hmm.
There is no reason why the whole proof and the whole result would not hold in the Neumann with the Neumann condition. So I feel that it's kind of technical restriction.
Yeah. Okay. And I also wonder if the argument can be extended to system of parabolic.
Yeah, very good question. So at least, well, I do not have the complete answer, of course, but a basic requirement that I would need certainly is to have a comparison principle.
Mm-hmm.
It is important. So already this restricts seriously, by the way, the class of systems that you want to deal with. Otherwise, if you don't have any comparison, I think it's much more difficult. Much more difficult.
Okay. Is there any other question or comment? Okay, if not, thank you very much again for your very nice talk, Emmanuel. And